hello everyone, and welcome to my talk. And thanks for Prometheus community for giving me this opportunity, and I'm pretty excited to be here. And my talk will be about aggregating metrics in flight. So my name is Roman, and I'm a software engineer. And the last couple of years, I'm working on the observability project called VictoriaMetrics. It's an open source project similar to what Prometheus does. And it has the similar application areas. Like it can be used for application performance monitoring, for infrastructure monitoring, for collecting metrics from Kubernetes deployments, etc. And as Prometheus, it also shares the same kind of problems and vulnerabilities as many as any other database, time series database that I know. So in order to engage the conversation with you, I have a quick question. How do you guys deal with high cardinality issues? Yeah, I didn't expect the quick answer on this. This is, of course, very complex topic. So let's start from the basics. What is cardinality? That's basically the number of unique time series that you store in the database. What is high cardinality? It's when your database starts to become slow or even unreliable. Why high cardinality matters? Because if your database is slow, it means it is not reliable anymore. You can't have a critical path depending on this monitoring solution. So you either need to do something with the data or pay extra money to add more and more and more hardware to deal with the high cardinality. And if you try to Google what to do with the high cardinality, you will probably find a bunch of articles, and they will suggest the same steps and the same actions to take. So they will recommend you that you need to find the source of high cardinality metrics, assuming that all of your sources are OK, and only one of them is exposing high cardinality data. So you need to find it, and you need to optimize it. And what are the optimization steps? Well, you can use relabeling. That's the Prometheus native feature. You can drop some series which you think have high cardinality, or you can drop some labels which contribute to cardinality. This is a cool protective approach to do this, but the problem with that is that when you drop in the metric, the time series, you're losing the information it brings. So maybe you needed that information, but you're dropping it. And what is even worse, you can drop the high cardinality label. And if you know, the unique label value pairs is what makes time series unique. So if you drop in some high cardinality label, you lose the ability to distinguish between different time series. So in the result, you have matrix collision instead of reducing cardinality. Another cool approach is to find and modify the source of the high cardinality data. So it assumes that you can find the specific exporter which messes things up, and you can patch it to change the logic, to apply some tweaks to aggregate data or whatever. But this is usually not the case, because as a monitoring platform maintainer, you likely don't have access to users' applications, to users' exporters, etc. So you just don't have authority to do that. And the third approach is to use recording rules. And it's also a native Prometheus feature introduced by Prometheus, and let's dive into details what it is. So recording rules, according to Prometheus documentation, helps you to pre-compute frequently needed queries, so they will be performed faster next time when you execute them. And here's how a recording rule works. So it's super simple. You have only two fields to configure. The first one is expression. That's basically the query you want to optimize. In this case, I picked one random query. And the second field is a record. That's basically a new name that you give to results of this expression. If you, let's do a quick demo how this works. So I'm taking this query, and I'm executing it in Prometheus. I want to optimize it, so I'm making recording rule. So here's what I do. I execute it in Prometheus UI. I'm getting this result. And this result is basically aggregated result of the queries that I made. And recording rule does exactly the same. It takes my query and executes it periodically with specific interval. Then it gets the result of this query expression, adds a new name to it, and stores back to the Prometheus storage. So later, on query time, you can use your record name instead of running the actual PromQL query. And it will give you results very likely much faster, because it will just touch less data and will not need to do extra computations. Conceptually, recording rules look like this. You have a time series database, and you have a data flow, which you ingest into time series database. And then you have a ruler, which executes these periodic expressions and backfills the results back to the time series database. Of course, in Prometheus, ruler is a part of the main process, because Prometheus is a single binary application. But in some distributed systems like Tanos, Mimir, VictoriaMetrics, they are distributed. There is no one single process which has access to everything. So ruler in these systems is something separate service. And it uses the public APIs for query and for write. The issue with recording rules is that no matter what you do, if you use recording rules, you will store more data, because you store the raw data and you store results of the recording rule. So no matter what you do, you will store more. And another problem is that recording rule has nothing to do with the data ingestion flow. It doesn't control it. So it means that you can't deal with high cardinality or churn rate using recording rules. What would be great is to have some solution which will help us to extract the information we actually need from the whole data stream, to extract only that data or in that form that will be useful for us or for users. Something in the middle between your clients, between exporters, between applications, and your time series database. How we can do this? Well, we can use Prometheus. We can use chained Prometheuses when the first Prometheus is used as a protection barrier for you. It scrapes all the data from all the applications that you need. And then it has a set of recording rules where you describe how you want to transform your data, whether you want to calculate aggregates, or you want to downsample or transform the data, whatever. And then you forward this result of this recording rules to the central Prometheus, or public-facing Prometheus that connected to Grafana, and people use it for running queries. And it's expected that these aggregated results will be very fast, will have low cardinality, so you're protecting your central public-facing Prometheus. If something bad happened to your exporters, for example, cardinality explosion, just bad deploy or whatever, the first hit will be taken by this Prometheus in the middle. So you can do this. The downsides of this approach is that if you run Prometheus on the high load, it will likely take a lot of time on restarts because of the wall replay, but you probably would like it to start immediately without skipping the aggregation intervals. And the second one is that Prometheus is the full-fledged time series database. It has many processes inside for storing, indexing data. So you will have an overhead for preprocessing data. It is very likely you can avoid that overhead if you don't need to maintain this full time series database flexibility. And for this to not be just empty words, I did a test, and I compared Prometheus and stateless agent collecting metrics from VictoriaMetrics ecosystem. They doing the same work here. They sharing the same config. They scraping avalanche instances at a rate of 130K samples per second. And they forwarding the only aggregated data. So Prometheus has one recording rule which flushes everything into one rule, into one time series. And VM agent uses stream aggregation to do the same stuff. And you can see they're doing the same work, but the memory difference is about 4 times. Prometheus takes 4 times more memory for doing the same work, just because it has this overhead. What can be done for this? So the idea of pre-aggregating data is not new. It was actually created in 2014 by Brian, and it was called can we have a scrape time rule evaluation? That idea wasn't implemented in Prometheus, but there are some traces of it. So in the Grafana agent repo, there was a different ticket to add middleware to perform aggregations between scrapes and storing. And later, the same issue was created in Grafana Alloy, if I'm not mistaken. But still, there is no way how you can do this pre-aggregation without using the storage. And here we come to the stream aggregation concept, which is now one of the open source features that VictoriaMetrics collector provides. So the concept of stream aggregation is super simple. It's very similar to recording rule, but the difference is that metrics collector stands between time series database and the data ingestion flow. And it can perform interval evaluations before data gets into the database. And having this ability, you can control what data goes after the collector to the time series database. So stream aggregation allows you to aggregate incoming data by 2 dimensions, by time and by labels, before data gets written into the storage. As I said, it's open source. It's supported by VictoriaMetrics metrics collector called VMagent, and by VictoriaMetrics single node installation, which is like a Prometheus, a single binary TSDB. Here's how stream aggregation works conceptually. So you have this data stream of time series ingested, and then you have this blue-shaped rectangle, which is stream aggregation. It has 2 params. The first is the time interval, which is x-axis, and the second is the matcher, what time series I want to aggregate. Periodically, once per interval, it aggregates all the data it accumulated and produces the aggregated results. And then you can decide what you want to do with those results, whether you want to forward them to one destination or to another. Here's how the configuration looks. It's more complex than recording rules, but still not that much complex, I would say. So you have 4 fields here. The first one is match, like what time series, what metrics I want to aggregate. The second is interval, on what interval I want to do the aggregation. And then you decide by which labels you want to aggregate. You can also pick by labels or without labels. And you decide on output, it's a type of aggregation you want to apply. Here we apply an aggregation output total, which is meant to deal with counters and support this counter reset feature, etc. In result, if you apply this configuration to VMagent, it will produce you a new metric, as well as a recording rule. This new metric will have the prefix of the original matched metric name, and the suffix of this metric will be the encoded stream aggregation config. So it says that it was aggregated on 1-minute interval by this label, and the aggregation output was applied total, similar to counters. So a bit more details about these config params. So match supports actually a list of selectors, and it's the full functional time series selector. You can use regular expressions here. You can do match series as you do with PromQL. And by default, stream aggregation will drop the original data. So you get only aggregates, but you can override that to set command line flag called keep input. And then you will have raw data and aggregated data. And you can, for example, split them between 2 destinations. The outputs, so it supports a multiple aggregation outputs. You can also specify multiple aggregation outputs, but per one matcher. And here we support the classical stuff like mean, max, average, count samples, count series. We also support rate, deviations, etc. On our documentation, you can find examples how each this output can be translated to typical PromQL metrics QL query. And then you have these ways to aggregate data. So you can aggregate by time, and you can aggregate by labels or exclude some labels from aggregating. So here you can control this churn rate. If you aggregate by specific label that you know you need and you trust, all the extra labels will be summed up or aggregated in the runtime. So what opportunities this stream aggregation config on the metrics collector gives us? Well, the first is reducing cardinality, and most important feature from my perspective. So to do a little experiment, I go to the playground, which is basically sandbox, VictoriaMetrics sandbox, publicly available. Everyone can try it. And I found the most expensive metrics that we have right now in terms of series. This metric is by, for some reason, is a histogram, of course. And this histogram takes 15K unique time series per day, and it's about 7% of the total value of series that are stored on the playground. So what I can do with that? Well, I can write this stream aggregation config, so I can match this specific time series. I can define that I need 5 minutes aggregation interval, and I want to use rate. And to dimensions, my dimensions will be resource, verb, and of course, bucket label. This will be transformed in the following metric name. And then, on query time, I can do this. So here we have comparison of the row query, which uses the row samples. It's a first query, which calculates histogram quantile 19th percentile, whatever, over this metric. And the second query also calculates the same, but it doesn't do the sum rate. It uses the result of stream aggregation. The results on the plotted results are very similar. It will be enough for my alerting rules. It will be enough for my dashboards. But the difference in execution time is almost 8 times. So the first query that uses raw data executes 11 seconds, and second query takes 1.5 seconds. What else I can do with stream aggregation? Well, I can downsample my data. So I can simply match every counter that goes through my VM agent according to Prometheus naming convention. Everything that ends on the total or bucket suffixes is a counter. So I can match that. And I can say that I would like to downsample it on 5-minute interval, and I want to calculate min, max, count samples, and sum samples. In result, I will get this downsampled series that I can decide what to do next after that. This will not reduce the cardinality, but you can combine it with grouping by labels. What else? Deduplication. So the common pattern right now in observability is that every target needs to be scraped twice, at least for high availability purposes, which means that there is a duplication of the data that you send to some remote storage. VM agent supports the duplication interval, where it can pick only last sample on specified interval for every unique time series. So in order to reduce the pressure on your time series database, you can simply add this command line flag and set that, hey, I want to deduplicate everything on scrape interval, for example. If you scrape at 30 seconds, then you need to deduplicate on 30-second interval. And this will reduce twice your data flow. What else? Aggregating, stream aggregation works for all data ingested into VM agent. It could be scraped data, it could be influx data, it could be open telemetry ingestion. It has access to everything. You can some counters receive from open telemetry and some counters receive from scraped targets, and then send it via Prometheus remote write protocol to external time series database. And what is cool about this is that you can send it to Prometheus as well. You can send it to Tanos, you can send it to Mimir, to VictoriaMetrics, because it's the same protocol. What else? VM agent gives you a bit more flexibility on how you control the stream of data, the pipelines. So it has this global ingestion pipeline where you can apply global relabeling rules and global aggregation configs. And then you can configure stream aggregation VM agent to forward data to multiple destinations. So you can specify 2 different URLs, 3 different URLs. And you can say, well, replicate this data across those URLs or shard data across those URLs. And you can specify separate relabeling and stream aggregation per each URL. And it will be applied differently. And of course, what is very important with stream aggregation is it worth it? Is it actually cheaper than storing the data in the database itself? So here, another experiment on the same prom scrape configs that I made with Prometheus, but here I'm running two VM agents doing the same work, but one VM agent extra does stream aggregation as well. So they scrape 130K samples, they push 130K samples, and one VM agent additionally aggregates 130K samples per second in real time. And here's the difference in resources. So VM agent, which does this stream aggregation, will take 1 more CPU and 1 more gig memory for doing this work. What challenges we faced with stream aggregation? Well, memory usage, unfortunately, the same as I showed in Prometheus. But it showed itself only in specific cases where we had to deduplicate or calculate uniques over data with high cardinality. So basically, if you scrape 1 million of unique time series, you have to store at least one sample per each series in the memory in the process memory, because you don't have access to the time series database. You can't put this data later, then index it, and then search it. No, you have to store it in the memory. And every sample contains the following fields. Well, you have this value and timestamp tuple, and you will have, which are pretty predictable, right? They both consume 8 bytes. So if you store, for example, 1 million of unique time samples, you will need 16 megs of memory. That's not that much. That's pretty easy. But labels are unbounded, and on average, from Kubernetes targets, you scrape about 25, 30 labels per series, and those labels can have arbitrary lengths of values, and you will have to store it everything in memory, because otherwise you won't be able to distinguish between unique series. So storing labels in the memory results in the memory problems when you scrape targets with big number of unique time series. What we tried to do with that? Well, we tried to store not slices, but concatenated string, which didn't show much benefit. We tried to use hashing to make it predictable, so big labels will be hashed to the limited label size, but that's a bad idea because you can't unhash it back, and you will need to unhash it back when you push to remote write protocol. And it also can result into collisions because no hash is collision-free. We also tried to compress this in the memory using that standard, and it wasn't efficient, so I tried to train a custom dictionary based on Kubernetes metrics and node exporter metrics and cAdvisor metrics. It improved compression, but still the CPU cost of compressing everything and decompressing everything was too high, so it wasn't worth it. So we decided to do some custom compression, and it's very simple. It's similar to string and turning, but a bit different. So as you know, every time series is unique because of the unique combination of label value pairs. So what we do, we maintain a compress table. Every time we see a unique label value pair, we encode it with the after incremental index. So we basically maintain some index given to each unique label value pair, and we stored it in the table. Encoding this time series would mean that the time series you see on the screen will be just expressed as 0, 1, 2, 3, the 4 uint64 digits. Using variant encoding, we're reducing it on average by twice, so 16 bytes per this time series. When we see a new time series, we add to the compressed table only that label value pair that we didn't see before, and we encode it as 0, 1, 2, 4. So very similar. But the cool thing about time series is that most of your labels are usually constant. Labels like job or instant, they do not change that much. They will likely with you for days, weeks, months. But there is only 1 or 2 small labels like pod label, which makes this high cardinality problem, which changes on every deployment every day, which produces all these high cardinality problems. So storing only this compressed table, using this compressed table, we can store only this. It will grow really slowly. That's what I'm trying to say, because you will record only those labels which never seen before. And the compression also looks very simple. You just decode it and read 8 bytes, look up in the table, return the result. Simple. Here's how it looks in the code. So we maintain 2 sync maps, one matching label to index, which we use for encoding, and the second map matching indexes to labels. That's a reverse table because we need to decompress this time series before pushing to a remote write. And also index generator, which contains this auto-incrementing stuff. So here's how compress flow looks like. We received a bunch of labels that we need to compress. We go one by one. We do a lookup in the compressed table. If we find entry, that's the fast pass, we just return this entry, attach it to the slice. If no, we need to increment the counter and we register it again. And this counter here is pretty important because when we start this counter from 0 to something like that, that's the most efficient for variant encoding because all these counters, they're condensed next to 0, and this is when variant encoding is very efficient. The compress is also simple. We loop through the labels. We make a lookup. Yeah, so after we added this label compressor to the VM agent, we reduce memory by up to 5 times at the worst cases that's on production data. And of course, this label compressor used across all the aggregation inputs and inside the VictoriaMetrics as well. So it's like a global state, which helps to reduce the memory. Yeah, and a few words about scaling the stream aggregation. So VM agent supports the sharding feature, where you can specify how you want to support by which labels. And that means that you can structure the B-level architecture of VM agents which collecting data, and then they sharding data across aggregation layer. And here you make sure that every aggregation VM agent will get its fraction of the data, which can be safely aggregated without collisions. Yeah, so a summary. Stream aggregation allows you to control the data flow before it gets into time series database. It helps you to control the churn rate, which is the biggest abuser of modern time series database, from my experience. It has low resource consumption compared to other solutions. It helps you to scale horizontally, and it's open source. You can use it together with Prometheus or with any other tool which supports Prometheus remote write protocol. That's all. By visiting QR code, you can get access to the slides. You can also check the additional information. Here you can find, for example, source code for label compressor. You can find the snapshot of Grafana dashboard that I showed on the screens to investigate more metrics if you're interested. And that's all. Thanks.
Small gift for you, and yeah, who has some questions? Amazing.
Cool, thanks for the presentation. Actually, I have 2 related questions. First one is, like, can we specify what is the label it's going to be used by the duplication, or it's like a static label?
No, because it won't be a duplication. Actually, it's a different. I know that Prometheus does the duplication on specified labels, but in VictoriaMetrics, duplicates are identical time series. You don't need to specify anything. It just, if it sees the conflicting samples, it will deduplicate it.
Okay, okay. And question like, how did you handle the use case where you have like samples going to different VictoriaMetric agents, for example?
How do I aggregate them correctly?
Yeah,
well, by
duplicate in this case, like for example, imagine you're scraping, you have a high available agent, they are scraping, and they are remote writing to another agent doing the duplication. How did you ensure that the samples are going to the same?
Yeah, you deduplicate before you split the data stream.
Oh, okay, okay, thank you.
Hi. So one thing that I've always struggled with when trying to aggregate, the dimension that I want to aggregate away the most is the instance. But if I'm aggregating counters across multiple instances, they all reset at different times. How are you handling that? Tell me your magic.
Well, every unique counter that you see is maintaining counter reset function individually. So VM agent will store this unique time series definition in the memory. And if it sees that the next value is lower than the previous value that it already remembers, it will understand that this is a counter reset. So it will return the actual result back, and only then it will do the aggregation. This is how it works.
So it's kind of like create timestamp feature, right? A bit. Might optimize this case a bit for you.
Yeah, probably yes. I'm not really familiar with this feature.
Okay. Who has a question? Arthur, do you want to add?
Thank you. You mentioned the aggregation interval. So does it mean that, let's say, if you have an aggregation interval, or you're trying to aggregate over, let's say, 5 minutes, does that mean that your data will be delayed by those 5 minutes?
Yes, sure. But This is how it works. If you aggregate by, if you downsample or aggregate by 5 minutes, it means that the resolution of your data will be 5 minutes. One sample per 5 minutes.
Yeah. And second question, is the downsampling feature also available in the open source version?
Yeah, everything that I showed is open source.
Thanks.
Arthur, you have someone behind as well?
If I remember correctly, all VictoriaMetrics binaries, they have on SIGINT gradual shutdown. Does it support this as well? Would it wait for all timeouts to stop?
Yeah, that's a good question. That means also that aggregations, that if you configure aggregation interval, for example, 15 minutes, and you need to shut down VM agent, what happens with the aggregate state? So we have a feature request which will eventually will allow VM agent to dump the data on the disk when you want to shut down it, and on the start it will reread it and restore the state. So far, you have two options on the aggregation right now, either to drop data or send it as it is. Send it as it is works okay for aggregations like max, for example. So you calculate in the max value on the interval, you can send it right away. But if you calculate increase, it's not the same. So it's better if you use increase on 15 minutes interval, you'd better to drop this data right away. And you can configure it per each aggregation output.
I have one. So we have open issues in Prometheus about how memory usage in Prometheus agents is not optimal because we have write-ahead lock. As I can see, in VM agent, you don't have it,
Yeah.
but you have interest because of the what was just asked. You need a write-ahead log. So when VM agent restarts, but you need data for long, then you use write-ahead log. Is that correct?
No, it is not completely correct because write-ahead log records every distinct operation, and we don't need this. We need to just dump the current aggregate state, which will contain, very likely will contain much less samples. So it will be different to write-ahead log. It will consume less disk space.
All right, thank you.
Okay, one more, Arthur.
This map, how much it grows, you don't clean it, right?
Yeah, actually, that's a very good question. We tried to clean it. So those maps, they never cleaned. And it was a pretty big concern. I was thinking about how to atomically clean this map because you have two sync maps that you need to atomically clean. And later, there was a good idea to not clean it and see what happens. So what happens that at max, we've seen on production rate of ingesting 1 million samples per second via VM agent. After 1 week of data, it was consuming like 20 megs of data. So it was a very simple solution, just do nothing.
Okay, we are unfortunately out of time. It's time for our quiz. So thank you so much for amazing ideas.
Thank you.